Any questions? Okay, so we'll move on then, right? So yesterday we talked about another exercise, right? We did a exercise on um, we talked about a game, right? And the challenge was to design uh, a small hardware which will check the user's guess, right? And the secret that the computer has guessed, and compare them and provide feedback on the guess, right? So that the user can improve the guess in the next, right? So that is what we considered. And did you guys think about how to test that? And did anybody try to write some test vectors? Practice will help you. Okay. So anybody tried? Only the genware. What does it mean there? I don't know. Oh, you don't want. So genware is not clear to you. Is that what you're saying? Oh, okay. All right. Let me explain that. And somebody is saying I did not use the index that was used. Okay, fine. I'll explain that. I hope you can see my screen now. All right. See, remember on day one, we had done a. Uh, okay, let us do an incrementer. Let us do a new one, right? So, what is an incrementer? It takes as input a n bit number, right? And adds one. That's all, right? So, let us keep it simple and let us assume that it is a 4-bit incrementer. Okay, so it's a 4-bit incrementer. It takes as input a number A and produces a number B. So input 3 to 0 A and output 3 to 0 B. So B equals A plus 1. That is what should happen. Okay. See, if you just want behavioral code, okay, then all you have to do is you can say always at A, B equals A plus 1. Okay, this will work. Okay. So we'll try here. Incrementer, instance, incrementer, AB. Okay. Then initial, begin, end. So initially, let us say we set A equal to 5, then display A equals and B equals. Okay. So this is a very simple test. So you can see it increments. Right? So I gave 5 as the input and it was able to increment and show 6. So similarly, if I try 9, it will possibly show me 10, right? And last but not the least, if I show 15, right? What do you think will happen? Okay. It will show 0 because 15 is the largest number we can represent using 4 bits. And when I increment, the carry will be generated, but we are not displaying the carry, so it will show as 0. Okay. So designing an incremental using behavioral way of things is not difficult, right? But suppose we want to design it like a hardware engineer does, right? So this is okay for the verification purpose. Okay, I may be quickly interested in generating an incrementer. So this will possibly do the job. And maybe synthesis tools can do this in a reasonable way. Okay. But sometimes, see, we want to do, like we have other considerations. Okay. So let me see whether I can show it in the slide. I have this new thing that I'm trying to use. So, see, how do you design an incrementer, right? Suppose we have, oh, how does it work here? See, suppose I have 1101 and I add a 1. The incrementer output is 0 1 1 1. Okay. If I have 1110 and if I add 1, I get 0 0 0 0 3. So this is what an incrementer is. So I could ask you to do it like a usual combinational logic, right? I could say the input is, I can write a Karnaugh map, right? One for each of these. Let us say this is called A3, A3, A2, A1, A0. Let us say this generates B3, B2, B1, B0. And I could write Karnaugh maps. I'm not doing a great job here. So if you draw 4 Karnaugh maps, one for each of these B3, B2, B1, B0, I'm sorry. It's very clumsy. So when the inputs are all zero, the output is one because we are incrementing. This is one, so when you increment, it will become two. This is three, so increment will be four. Okay. After increment, it will become four. This is, I believe, two, so after increment, it will become three. And then this is so this is, I think, four, right? So zero, one, zero, one. Five is zero, one, one, zero. And I think this will be seven. So this will become eight. And this is six, so it is seven. Okay. And so on. So you can fill all these, then write down expressions for B3, B2, B1, B0. Okay. So you can go through that whole exercise, right? And then you will write assign statements for each of them, etc. Okay. So that is one way of doing it, right? Unfortunately, what will happen is it will not give a very regular layout. Okay, you will get all kinds of expressions. Okay, you can give it a try, and you will realize that it will give a fairly. So we want to come up with slightly better logic. Okay, so remember that what is a one-bit incrementer? Anybody knows what is a one-bit incrementer? Why this pointer doesn't come where I need it? See, a one-bit incrementer is a half adder. Okay. So a half adder takes two bits, okay, adds them and generates a carry. So this is a half adder. So let us say I take the number that I want to. Suppose this is the number I want to. To that I want to add one. So I can give these two to a half adder. So let us call this A0, and this is the logic one. That will generate B naught, and it will generate a carry. That carry will go as input to A1 and will get B1. Okay. So I will be able to do this with half adders. Is that clear to everybody? How we can create an incrementer? This is logic one. This is output carry. Okay. So is that clear? What does it mean? They, when you say output is flipped, see, agile Matthew. See, you are saying 4-bit adder can be used, but it will be an overkill, isn't it? See, a 4-bit adder will have full adders here, right? So we don't want to do that. Okay. So that's the reason why we don't need any full adder. We only need half adders. Right. Everything is a half adder. Okay. The advantage of this design is that it is regular, and as a result, it will be you can design one module and repeat it, right? So even in the layout, it may be much easier to do than so in circuits we prefer these kind of regular layouts. Okay, so let me go back to this guy, right? And let us design the incrementer in a different way. So I will have to use, let us say I'll create another module called half adder, which takes as input 2 bits. Let us say we call it in A and in B, and generate sum and carry. Okay? And you may know this. Sum is nothing but um, anybody remembers the sum expression? It is nothing but the XOR of in A and in B. Think about it. When I add 0 and 1, output is 1. When I add 1 and 0, the output is 1. When I add 1 and 1, the output is 0. The sum is 0. Okay. So, and finally, when we add 0 and 0, the output is 0. So, this is nothing but an XOR gate, right? Similarly, assign carry. Okay. I believe it is the OR gate or the AND gate, possibly, right? Because we get a carry only when both the bits are 1. Okay. So, this is the half adder. So, we can take many half adders. Okay. So, we could take maybe half adder, let us call it as HA0, and connect A0, right? But before that, I had to write input 3:0 A and B. Right? I will take a half adder and connect A0 to it and logic 1 to it. Okay, logic 1. And then the output is, let us say, a temporary, I'm sorry, B0. Okay, and the carry goes to some temp. The next half adder will take A1 and temp 0, generate B1 and temp 1. Then the another half adder will take A2, temp 1, B2, temp 2. And the last one will take HA3, A3, temp 2, B3, and final carry. Okay, so the final carry is so these wires that we can declare as temp 0, temp 1, temp 2. If you want, we can call it temp 3 also. See, if instead of imagine that this was a 16-bit adder, right? Then I'll have to write many more statements. Okay, I'll have to write a lot of statements. Okay. This will work. You can verify that this 3-bit adder will work. Okay, let us try to compile it. We can see that the same thing is happening here, right? See, it is giving an, this should be 1B1. Okay, it is saying you are connecting an integer which is 32 bits. Okay, see, it is behaving exactly the same way. I can try maybe 13. Okay, so it's the same thing. But suddenly, if I decide that all of them must be 15 colon 0 or something like that, it will be too much work. Okay, that is where generate helps. Okay, so we can write a generate statement, right? And say genvar I, okay, and generate. And what is it that we are generating? We are generating a half adder, and here we'll write a for loop. For I equal to 0, I less than 4, I equals I plus 1. So in this for loop, we are expanding HA. Let us call this half adder. Here I had to, instead of A0, it will be AI. And we'll write B0, BI. Okay. Now, what do we write here and here, right? If you want a sort of a neat solution, right, where everything is expressed in terms of I, so maybe we can have a array of wires. Okay, we can call it maybe 4 to 0 temp, and we can say that the input comes from temp 0 and goes to temp of I plus 1. So everybody understood? We are unrolling this loop. It is nothing but whatever I did earlier. There is no difference between this and the previous one. It is just a different way of doing it. Okay, for I equal to 0, I less than 4, I equal to I plus 1 means when I equal to 0, it will say HA half adder A0, temp 0, B0, temp 1. That means take A0 and temp 0 as inputs, generate B0 and temp 1 as outputs. The next half adder will take A1 and temp 1, generate B1 and temp 2. Now temp 0 is nothing but logic 1. So we can assign temp 0 to logic 1. And the last temp, okay, when I becomes 3, it will be temp 4. If you are really interested in the output carry, that will be the carry out. So this is an incrementer which takes A and B, which are 4-bit numbers. This is a carry output. And we created some intermediate wires. Okay, why do we need 5? Because you can see the diagram, right? In the diagram, see, this is temp 0, this is temp 1, temp 2, temp 3, and temp 4. Okay. Temp 0, I'm going to connect to 1. So the first stage or the 0th stage takes A0 and 1, adds and produces B0 and temp 1. Right? This is temp 0, this is temp 1. A1 and temp 1 output is B1 and temp 2. A2 and temp 2 output is B2 and temp 3. A3 and temp 3 output is B3 and output carry. Output carry is also called temp 4. Okay. So this way, whether it is 15 bits or whatever, it doesn't matter. As a matter of fact, you can even have that. Right? So I can say 4 here, right? And I think this should work exactly the same. Wait, wait. 7, there is an parameter. I think this is like this. And ideally, you should make this n minus 1. It should be n minus 1. It should be n. It should be n. It should be n. Right? So I have parameterized it, and carry on. Right? So we are getting the same thing. 13 is incremented to 14. Okay. Maybe we can increment, we can also print the carry. Okay. So in this case, the carry will be 0, right? Whereas when I make this, let us say 15, see, the carry is 1, right? Now make this, let us say 15, okay? And change this to 15, right? And change There was some glitch. Am I still audible?
You are audible.
Hello.
Audible, sir. You are
Okay.
audible.
Okay. Adit Varia, everything generate has to have a, yeah, only then it makes sense, right? See, if there is no for loop, then I don't get any advantage. The reason why we have done this generate and generate is we don't want to write so many statements one by one. That is why we are doing it like that. Yeah. Okay. Any other questions? Good. I think Adit asked a good question. So I will give this as an exercise for you to do a similar thing for a that full ladder subtract. Okay. So here is an exercise for you. I'll send this to Professor Vineet Savula anyway. This is day 4. This is incrementer using generate state. Okay, and the exercise for all participants. Use generate statement and write a description of a 4-bit added subtractor, okay, and test it exhaustively. Okay, just like we did earlier, we have done this exercise, but we did not use the generate statement. But this time, please use generate statement. Okay, so this is an exercise for you. Any questions? Can't we write for loop without generate? No. If you want, you can do it other say for loop for the purpose of generation of hardware, you cannot do without generate, right? Otherwise, for loops can be used. We have used for loops before, right? For loop for generating hardware statements, you cannot use without generate. Okay. Right. Let's move on to maybe designing, let us say, a counter, right? So I want you to design a counter, right? Which is, let us say, modulo 10 counter. So design a modulo 10 counter. What does it do? Modulo 10 counter. What is the purpose of the modulo 10 counter? How many bits are in? Okay, counts 10 times. All right. See, that is not, it's, I think you are on the right track, but I don't know what you mean by counts 10 times. See, it counts this sequence 0, 1, it generates this sequence and then it resets. So it goes from 0 to 9 and then it resets back to 0. Now to do this, again we have to write a module. Okay. So let us say we call it counter modulo 10 counter. So what are the inputs and outputs to this counter? Okay, how many the counter output will be? How many bits? How many bits will be in the out of the counter? Correct. So Manjunath is correct. Okay. So it has 4 bits, right? Because we have to represent all these numbers, right? 0 to 9. So to represent 9, you need 4 bits, right? So you will need count out is 4 bits. What about the inputs? What inputs does the counter need? See, the counter needs the clock, correct? Right? So you need a clock, right? And you also need a reset. See, unless you can reset it, then you don't know where you are, right? When you start, you should have a reset pulse. So input, clock in, reset. So this is our input output interface. Is this a sequential circuit or a combination circuit? Correct. It's a sequential circuit, right? Because see, these are all states, right? The counter is in state 0, and because it remembers it is in state 0, it will go to 1, and from 1 it will go to 2. So it needs that memory. Yeah. So that is the reason why it has to have a. Uh, so we will need to keep maybe as many registers as there are count this one, right? Let us say we call that a state. So we'll need a 4-bit state register because there are 10 states. Okay, to represent 10 states, we need 4 flip-flops. Okay. So as a result, we will keep 4 bits. So there are 10 states. Need 4 flops. So normally we write things like always, at, right? And we are normally used to writing the inputs, right? Here, let us say clock in and reset in, right? So if I do that, it will respond to every state in clock and reset. Okay. If clock goes from 0 to 1 also, it will respond. If clock goes from 1 to 0 also, it will respond. Similarly, reset. If it goes from 0 to 1, it will respond. So it will keep responding to every state change. See, we may not want that. We may want it to only be sensitive for, let us say, pause edge of clock. Okay. We can also say it should also be so pause edge clock in means an event that gets triggered when clock goes from 0 to 1. Pause edge reset in is an event that gets triggered when the reset goes from 0 to 1. So this circuit gets triggered, okay, whenever either of these happens. And we have to decide how to handle these two, when the reset is triggered and when the clock is triggered. Between the two, reset takes higher priority. So we check that first. So if reset has become 1, right, that means it has gone from 0 to 1 here because we are checking for this positive edge. Then we have to set state to 0. If that is not the case, then the state should be set to, we have to increment and take the remainder when divided by 10. So this is a modulo 10 count. See here, I am sort of using a behavioral assignment. Okay, I am not explaining how to design this. We need a circuit that takes a 4-bit number like state, increments it by 1, and then takes the modulo. Okay, that circuit I am not designing. Okay, so if you want to design that circuit, you have to do it yourself. If you are not willing to leave that to Verilog, okay, as of now, what will happen is when this synthesis tool gets something like this, it will try to design this circuit by itself. But right now, I'm not giving that. I'm just I'm not designing anything. I'm leaving it to Verilog to figure it out. And the test bench will be something like this. So we will need to instantiate one copy of this counter, mod 10 counter. Let us call that M10 counter or something like that. And in order to exercise it, I will need a reset, etc. So I will need an external reset. Call it reg reset main, reg clock main, or test, whatever you want to call it. And you will get back 4 counter output. Okay, so that should be connected to these guys, right? So we can say connect clock in to clock main, connect reset in to reset main, and connect count out to count out. Okay, so I have made the connections. Now I have to start testing by putting some values, right? So I can use the initial statement, okay, and start by saying, look, in the beginning clock should be 0. and reset main should be 0. Initially, they are both 0. Then I can wait for 1 unit time. So pound 1 means at time 0 we had initialized these two guys, right? At time 1 we will make reset main 0. I'm sorry, 1. So at time 1 we are sending it to 1, and at another time later we are sending it back to 0. So time 1 reset main became 1, time 2 reset main becomes 0. That clear? See, you are allowed to write any number of initial statements, okay? And they all run in parallel. So I can have another reset main, I'm sorry, another initial where I'm going to, sort of activate the clock. Okay. So let us say I want to have maybe I will try to test it for the first 15 or something like that. So I can say repeat 15 times. Initially clock is 0. Maybe I can do it here. So what we can do is we can say, look, let us take the period of the clock to be maybe 10 or something like that. So we'll say after 5 units of time, make clock main equal to 1. And after 5 units of time, clock main becomes 0. So two parallel tasks, one for the reset part and another for the um, sorry. So one for the reset and one for the clock. So reset went from 0 to 1 and came back to 0. So a small narrow pulse was generated on reset, and that will trigger our modulo 10 counter, and it will initialize it here. In parallel, initially clock became 0 at time 0, and then at time 5 it became 1, and at time 10 became 0 again, and then time 15 it will become 1, time 20 it will become 0. So this will happen 15 times. So I'm giving 15 clock pulses. And once the clock becomes 0 to 1, that is when our modulo 10 would increment the state. Okay. So we can display the state either here. So if you display here, the 0 will not be seen because we have already incremented the counter. Okay. If you put it here, it will also show the 0. Okay. We can check that. Okay. So when you run this guy, there's some problem. I think what I have done is, yeah, unfortunately, I never, this count out is not even connected. Okay. So I think we have to say assign count out to state. Okay. The state is getting incremented. Okay. But without this, I am not able to see the output. Okay. So that was the bug. So it started with count equal to 0, 1, 2, 3, 4, 7, 8, 9, and then it got reset. Okay. So I take my words back. See, it actually showed the zero thing. Okay. It displayed the zero because as soon as increment the positive edge, see the change has taken place, but we are immediately displaying it. Okay. So it is showing the old value. So that is the reason zero is also. Okay. So my mistake. It will also show the zero state, right? See, frankly speaking, when I had not done this, it should have shown me Z here. It should not show me zero because I'm connecting count out, which is hanging, right? The output count out is not connected at all, isn't it? It's hanging. So this should have given me high impedance. I'm surprised that it is giving me zero here. Okay, let us see what the cadence simulator does. Here, this guy also is saying zero. How? Rate is zero, but the count out is not connected at all. It's hanging. And here, count out is connected to count out, and this is a wire, right? So there is nobody to drive it. The only person who could drive it is this count out. And as a result, I expected it to say zero. I mean, I expected it to say Z here. See, when I say percentage B, it is giving. So there's something funny here. Percentage G seems to, not show correctly. This is the correct thing. You see, ZZ means it's all high impedance. It's floating. So the count out is not connected anywhere. Okay? Whereas I think even D will do the same thing. Percentage D will do. I think G guy is slightly weird. See, so I think we should not use that percentage G. We should use percentage D. That clear? So remove this, and then your counter will be driven correctly. Is everything clear to people? This should be after this because it is complaining that state is not yet declared. So that is why I think the other compiler didn't compile, did not complain. Is that clear to everybody? So you would have observed one thing: all simulators are slightly different. Okay, some of them are a little bit more forgiving in one thing, and some of them are very strict. So they are all slightly different. Any doubts in this? Today everybody is awfully quiet. Is it because it's all very easy stuff that I'm discussing? Any questions? All right. Okay, let us try designing another circuit where the count sequence is different, right? We suppose we'll copy this guy here. This is a counter. Exercise 3. Fine. So now let us change the count sequence. Okay. Design a counter which generates the sequence 0, 1, 2, 3, 4, 5, 6, 7, then 6, 5, 4, 3, 2, 1, 0. Then again 1, 2, 3, etc. How will you go about doing this? So it should go up to 7 and come down from. It's like a triangular waveform. It gives 0 to 7 and 7 to 0. Then 0 to 7, 7 to 0. So how do you design this? How many states are in this circuit? Fujita is saying there are 8 states. Okay. What about the others? Anybody differs? Are you guys following, or is it? I'm a little worried. Not following? Akhar says, Dave says 13 states. See, actually, see, 0, 1, 2, 3. It's obvious that these are all states, right? See, when I'm in state 0, I go to 1, right? When I'm state, when I'm in this state, I go to 2, right? But here I'm going from 1 to 0. Okay? So this 1 here and this 1 here are not the same. So there are two different states. Similarly, 2, here I'm incrementing, here I'm decrementing. Here I am incrementing, here I am decrementing. Okay. So 0, 1, up to this is 8 states, 9, 10, 11, 12, and 13, right? I think this is also a state, 14, and that's it. So I believe there are 14 states. Because when I am in state 1, I am incrementing, but here I am decrementing. So we can design a state with 14. So I'm sorry, there are 14 states. So as a result, the number of flops required will be, we'll need 4 flops. Okay, 3 will not be enough. So you may be misled to think that there are only 3 outputs. Okay, and as a result, 3 flops are enough. Okay, that is not true. Don't confuse the number of flops with the outputs like that. That clear? See, another way to look at it this is, when I am in there are two modes. I am either incrementing or I am decrementing. So one flop can indicate that. Okay. We can use one flop to indicate whether we are incrementing or decrementing, and the remaining 3 flops can sort of help me in the state part. Okay. So that is another way of looking at it. Okay. So we can do it either way. This, let us say, we call it triangle counter. What are the inputs and outputs? What are the inputs and outputs for the triangle counter? Clock, reset, and out. Correct. So clock in, reset in, and out. What is the size of each of them? Clock is 1 bit, reset is 1 bit. How big is count out? How many bits for count out? Why, Dave? Why do you need 4? Because output is only 3 bits, right? 7 can be represented in 3 bits, right? So output is only 3 bits. Number of flops required is 4. I agree, right? But the number of output bits is only 3. Okay. It's like an interview question. Okay. So we can ask such questions in the interview and confuse everybody. right? So we can keep 4 flops. See, one flop can indicate whether you are incrementing or decrementing, and another 3 flops can tell me the state. Okay. The This is always the same. Pause edge clock in or pause edge resetting. So this is like always going to be the same. There is no change. Any sequential machine only responds to clocks and resets. Okay. Abhishek, correct. 3 bits. Correct. So here, what do we do? If reset in, that means we have reset has gone from 0 to 1. Right? When state becomes 0, so we have to do 2 things. One is state should be made 0. And what else? One more thing somebody has to tell me. What else is required? Think what else is required? Count equal to 0, correct. Not count equal to 0. Increment, decrement is 0. Very good. That is Pujita is answering. Very good. So increment or decrement should be set to 0. 0 means increment. Okay. So we are assuming that 0 means increment and 1 means decrement. So if you want to be very precise, you can say incrementing is 0 and decrementing is 1. Okay. So here you can say increment. If it is not the reset, that means it must be the clock. Okay. Now we have to decide what state we are in. Are we in the increment decrement mode, right? Or are we in the you know are we in the increment mode or are we in the decrement? So here we can say something like if inc or dec equals incrementing. Here we may want to write 1b0. This guy may complain. When we write constants, you may want to clarify that it's a 1 bit 0 and 1 bit. Otherwise, sometimes you will get all kinds of warnings. So if it's incrementing, what should we do? State should be incremented. And no mod etc. required because 7 will reset to 0 by itself. So we don't need to sort of do any percentage etc. Else state is state -1. So this +1 and -1 are high level constructs. Like +1, what does it do? It takes a 3-bit number and increments it by 1. Here you are taking a 3-bit number and decrement it by 1. So from the verification perspective, these are all fine. Okay, we are not going to crack our head and understand how that increment is going to be done. Okay. To test it, we have to again have the same thing. Module, count, test. We'll have a triangle counter, and let us call it as TRCNT. We'll have a clock main or something like that, and reset main, and then we will have a count output, and these must be connected to our triangular. So clock main is connected, and reset main is connected, and count out is connected. Some people like to put all these things in different lines, and they will give you comments here. Like this is if it is not obvious, see, we don't have to write comments like this is the clock and all that. Okay. But in case this is not obvious, you can write. And in order to get the counter to start, we have to first reset it. So start by saying reset main equal to 0. Then after 1 unit delay, reset main becomes 1. After one more unit, that reset main becomes 1. Okay. See, we are allowed to do clock here itself. See, we can, in the same initial block, we can start doing the clock also. Nothing wrong. Okay. You can say something like repeat. In this, let us try 20 repeats. Again, let us assume the period is 10. Okay. So 5 units later, clock main becomes 1. And 5 units later, clock main becomes 0. And whenever the clock goes high, we will display the value. And one more thing we forgot, right? When do we change from increment to decrement? That we have not handled. So when the incrementer becomes 7, right? That is when we should go to decrement mode. So that I have forgotten. If state equals 3 D7, then in or dec equals decrement, right? Similarly, when the decrementing we get all the way to 0, we have to change it. If state it becomes 0, then in or dec is incrementing again. See, this is a subtle bug, right? We forgot this. If you had only tested it for the first few clock pulses, it looks fine, right? And you may incorrectly conclude that it's working. So try this and see what we get. This if has a begin here. This is always end, I think. This begin has an end here. Oh, I think there's an end. Okay. See, in the system Verilog, right? To avoid this problem, what you can do is you can say something like this: reset, and you can say reset. This is always right, and here you can say always. This is reset, so this should be reset, and this is incrementing, and here also we need entry. Else doesn't decrementing. So this is not allowed in very long. So if you try this in the tutorials point, it will not work. Okay, but here we are using system Verilog compiler, right? So it should not compile. Now we have made the same mistake again. We have forgotten to connect assign count out to state. Right? What was the error that I got? Okay. 0, 1, 2, 3, 4, 5, 6, 7. Then there is some problem. This increment decrementing is not correct. Incrementing there is some bug. Spelling error maybe, right? Incrementing. When you say it said something. Reset not really. So begin reset. Oh, you know what? This is end reset. Okay, this end reset is not labeled. I don't know whether it will allow something like this. So this is not allowed. It's allowed. There is a bug in my code. State is 0, incrementing. Um, if decrement is incrementing, then state is 1, and if state has become 7, make this 0. Okay. Else, I thought I'm doing it right. What is the bug? Hmm. Let us see. 0, 1, 2. reset. There is some. What is that reset? I even reset I have given you. Zero to seven. And then when seven becomes there is a subtle error. Went all the way to zero. It should not have gone there. It should have come to 7654. So these two states are wrong. I mean, this state is wrong. And I'm sorry, this state is also wrong. So these two states, it should not go down all the way to zero. As soon as it became 7, I am changing it to decrementing. And similarly here, see, when I reach 0, it should not have gone to 7. Right? So there is some transition problem. So somebody has given some answers. Sir, the limit should be 6. Huh? I should change it to 6. Okay, maybe he's right. And here, 1. Zero, 1, 2, 3, 7, 6, 5, 8, 9. Correct. I think they were right. See, when we read 6 itself, mm, when we read 6, you know what? He's right because see, we have used this non-blocking assignment, right? If it was a blocking assignment, then after that we are comparing. Okay. So see, if it was a blocking assignment, 6 will become 7. And then I was okay if I was going to compare by 7. But because we are using non-blocking, immediately when we test, we should test it at 6. Okay, similarly here. So that was a subtle bug. Okay, so we should use, if you had used blocking, you would have got, you know, you can try, if you replace it with blocking, you will get 7. Let me try. No, Hmm. Huh. Oh, wait, what happened to 7? Oh, this had to 7. See, if it was blocking statement there, then also it's okay. So 0 to 7, then 6 to 0, and then again. So, so when you use blocking statement, the simulator, after completing this, it, only then it will go to this. Okay, it blocks. So this equal to means, the simulator will wait for this to complete and then go here. But if you use non-blocking, right, it will increment 6 to 7, but right away it will go here. Okay, that is why it has to be 6. Okay, so if you are using non-blocking, use 6. If you are using blocking, use 7. Okay, so that was a subtle bug. Let us look at the other. Sir, state is declared 4-bit. What, ma'am? Where is it declared as 4-bit? Oh, here, you are right. I need this is 2 then. Okay. So my mistake. Nirmala, thank you for pointing it out. Okay. We don't need 4 bits for state. Okay. Because it's only 3 bits. What else questions? So the limit should be 6, correct? Uh, Nirmala is saying 3 bits. Sir, check state declaration. It is 4-bit. I think she has been trying to draw my attention for a while. And sorry, I didn't see all this. Purvesh also Purvesh also pointed it out. Um, I think Athar also pointed out. How should 3 bits enough for 14 state? Om Nayak, right? See, the output is only 3 bits, man. Okay. And we are connecting the count out to state. So state is only 3 bits. But we also have one increment decrement. So effectively, we have 4 flops. We are not doing any magic. We actually have 1 plus 3, 4 flops only. You understood? Om Nayak. Om Nayak. See, whether it is incrementing or decrementing is also a state, isn't it? So it's like the two things together form a compound state. Okay. I am incrementing and my state currently is 0. Okay. Is that clear? Where is Om Nayak? Om Nayak went away for having samosa. Any doubts? Okay. So this taught us something. I think many people, they didn't know how to look at the number of states, etc. I hope that point is clear. And that blocking and non-blocking also is something that you have to keep in mind. Okay. So the non-blocking statement doesn't wait. So as soon as it comes to this, it doesn't wait for this. It will go to the next one. So that is the reason why we have to check for 6. So if you want to make this a generic triangle counter, which goes not only from 0 to 7, but in general, it may go to, let us say, um, any value that required. Then you can parameterize it. How can I use this to generate a triangular waveform in a signal generator? What will I require? I want to use this circuit to generate a triangular waveform. Ujita, sir, we have only 8 states and does state register is 3-bit? See, there are 4 bits. See, you can see, no? See, there are 3 bits for state and 1 increment decrement. So together it is actually 4 bits. I'm just looking at it in a different way. Is it clear? Anybody else? I was asking some question when I don't know what I was asking. All right, anyway, I'll give you this. Okay. And I thought I'll show you. Let us also do this in iCarus and make sure it works for you guys. I don't want to take a chance because you guys may not have access to that KLC. It works here also. Okay. So one more thing I wanted to show you. One more question has come. Purvesh, sir, can you explain line 27 and 29? Okay. Oh, you want to know these? This is nothing, man. See, this in system Verilog, these are decorations that you can put. See, colon always means you can track where it ends and where it. See, there is no indentation, for example. So, suppose people don't indent their code properly, okay, then it is very difficult to read what is going on. So, this is the solution they came up with, right? So that you can find out where the see. Sometimes this editor it completely ruins your indentation. It keeps on adding tabs, etc. Is that the question you had, Purvesh? Anything after colon is like a comment, right? Beginning of always. You can put anything here. You can put it. You can call Purvesh, and but here also you should have Purvesh. But don't put Purvesh, okay? Is it clear, man? Got it, sir. Yes, sir. Good show. So what I was trying to tell you was, see, you can see the waveform. Some people like waveforms. Okay, I don't know why, but some people like waveforms. So if you want, you can say dollar dump file, dump.vcd. You have to add this statement. Okay, this creates a file called dump.vcd and dumps the information about the all the signals. Okay, and you have to say what are the variables that you want to put. So 0 means starting at time 0, right? And you can say TRCNT. So TRCNT is this, the instance name. Okay. And then you can say open EP wave afternoon. Okay. So hopefully that will display everything. So you can see that, it shows the waveforms. Okay. So this is the clock waveform. Okay. See, some strange reason clock is X. Okay. So looks like I forgot to initialize the clock in the beginning. Then reset was initially 0, then it went high, then it came down, right? And the increment decrement is changing like this, right? And then count output is 0, 1, 2, 3 up to 7, then decrement. Okay? State will be the same because it's the same thing. Okay? So you can use this if you want in case that helps you. Now the clock, why is clock 0? See, I have forgotten the clock here. Reset alone was set to 0. So you have to also set clock name to 0. See, it doesn't matter in a way because when you set clock equal to 1, even the x to 1 transition will be treated as a positive edge. So we got saved. Okay. Otherwise, it would have been in turn. So these are somewhat subtle errors to these are some subtle errors to catch. So this is a counter which generates the sequence 0, etc. I think now I got the question that I was asking. Hey, how do I actually generate the signal, analog signal from this output? How do I do? How many of you are in second year of undergraduate? Anybody has second year? I don't know how to. Let me see. Who has completed second year? Aditya. Okay. Oh, I'm sorry. Attendees, you all. Okay. Okay. There are a few guys who have just finished second year. Okay. How many finished third year? Okay. Not anybody. Three. How many have finished fourth year? I mean, about to finish, I guess. How many are about to finish fourth year? How many are MTechs? Not seeing any of them. How many are MTechs, guys? How many faculty? One person has raised. Okay. Okay. I think you guys are giving thumbs up, etc. I'm not watching that. I'm only looking at this. Raise your hand or whatever. Okay, never mind. Mm, good. Mm. So the answer I was expecting from you is that if you take the output of this, let me see if this thing works. So let us say we have this counter, which is a triangular counter. It is taking a clock as input and a reset as output, and it is generating 3-bit output. Okay. What should I connect here so that I get a waveform like this? I may not be interested in the Purvesh is correct. Purvesh is giving the correct answer. You have to have connected D to A converter. Okay. A D to A converter is a I'm sorry, digital to analog converter. Okay. So what it will do is when it looks at that 000, it will give a 0 volts. When it gets that 001, it may give you somewhat somewhere here. Then 2 it will give here, 3 it will give here, 4 it will give here, 5, 6, 7. Then again it will give you like this. And again it will go like this. Okay. So op amp to be connected to clock. Op amp to be connected. How man? How op amp to be connected to clock? Converts quite. So ADC can be given. I don't know. He is saying op amp can be used. I don't know how to use an op amp for this square to value. I don't have a square. I have these digital outputs. Okay. I have these digital outputs. I lost my cursor. Here it is. This is a 3-bit output. So I'm getting 000, 001, etc. These are 3 outputs. Okay. Digital outputs. So they will be of this form. So 0, 1, 1, 1, then 0, 0, 0, things like that. So to my knowledge, you have to use a DAC. I don't know whether you can use an op. How do you intend to use an op amp? Dave, how do you intend to use an op amp? Okay, never mind. If you have a answer, let me know. So you can try similar thing. Maybe you can generate a waveform like this if you want, right? Or you can try generating a waveform like this if you want, right? So those things you can try on your own. or slightly more. You can also try a this is called a sawtooth waveform. This is easy. This is nothing but count from 0 to 7. Again, count from 0 to 7. This is anyway you guys do. But you can try some of these things. So try to treat this as an exercise. Any questions? So what is a really challenging project would be that change that counter to generate different waveforms. Okay, in you can create a more complex counter which produces different waveform. Okay, so it's somewhat programmable in nature. It's a programmable counter so that you can program it to generate different waveforms. Okay, it can do triangle, it can do sawtooth. So try that as a small mini project. Okay. Any other questions? Any other questions before we move on? So in a way, we started talking a little bit about system Verilog, right? So system Verilog is a sort of a superset of Verilog. It can, uh, if you give Verilog code, also it will work. Okay. That's what we have been doing. Okay. So this EDA playground, it understands system Verilog. Okay. Because I think this compile option that comes as a fact, as a default option that makes it use system Verilog. Okay. If you remove that, it will act possibly as an ordinary Verilog compiler. Whereas this tutorials point, it is, to my knowledge, it cannot understand system Verilog. It can only understand Verilog. Okay. So because it says also that it is a Verilog compiler, right? In addition to whatever Verilog already provides, right? System Verilog has a few other extensions. In fact, it's a very big language. They have extended in a many different ways, right? So we may not be able to cover everything. Okay, it's not possible. So we'll try to cover some of the important things. Okay, among the data types that Verilog provides, we have integer, right? Everybody knows this, right? This integer in Verilog is 32 bits, right? We have already seen that. But you will understand that the integer, right? If I declare something as an integer and simply say display x, see it will print, oh, You will see that it printed 32 x's. Okay? The variable x is set to 32 x's. Right. So in addition, in the same way, you may be able to set x to, let us say, 32 binary z. Then it will print all z. So these are actual values. You can set each bit of x to either 0 or 1 or x or z. Okay. So there are four values. Okay. It's a four valued way. So each bit can be set four values: 0, 1, x, and z. So you can imagine that internally, it is not 32 bits. Okay. You will need 2 bits to represent each, bit of x. Okay. So they will need 4 bits because you will need, I'm sorry, they will need 2 bits for every bit of x, because it can be 0 or 1 or x or z. So this can be a little bit wasteful of space if you really have only zeros and ones. Okay, sometimes we are sure that we only have zeros and ones, and x and z's are not going to come. See, for example, if you are using a for loop and there you need an integer, something like this, then there is no need for you to have x, etc. in I. Okay. So in such a situation, system Verilog allows int. The difference between integer and int is int is truly only 0 and 1. Each bit can be 0 or 1. So here I can say y equals, if I try to do 32 z, okay, notice that it did not do that. Okay, it made it all zeros. Okay. Similarly, you can try setting it to x. Okay. So you will see that that also will not be done. Okay. So if you try x or z, it will make it zeros. But if you try one, of course, it will take that. So you can set the bits to zeros and ones, but if you try to set it to anything other than that, it will get changed to 0. And that behavior, whether it prints 0 or 1, may not be always the same for all compilers. See, some other compiler may do something else. Okay. But did everybody understand this? So there is a difference between an int and an integer. Int is not there in system. Int is not there in Verilog. This is a system Verilog construct. So use int when you are sure that you have only mm, zeros and ones. You don't expect any x's and z's. So you have to use it carefully. Okay. If by chance you are actually going to get x's and z's, then this will happily print zeros, and you will think that everything is working. You understood, no? This can be a serious, bug problem. I don't know why they have given all these things. Their reasoning is it saves space, right? But you have to be very careful, because the actual output may be buggy. It may be actually having x's and z's. But if you ended up looking at it as an int, it will print zeros. And I don't think even a warning is issued saying, say, ideally it could have given a warning here. right? When I try to put Z here, it could at least tell me that, I'm treating it as zero, but I don't think any warning was issued. Okay? I don't think even Cadence will do that. Yeah, I didn't see anything. Okay, there's no, it didn't say that. Okay. Is it clear what int is? In the same way, you have short integer or short int. So short int is actually 16 bit. Okay. Short int is actually 16 bit. So it will give you a 16-bit number. And it behaves exactly like the int, only zeros and ones. This is useful because sometimes we don't need a 32-bit number. See, we write small loops. In such situations, you may not really look for anything big. They also have byte, that is for an 8-bit. Here I should make it 8 actually. Okay. See, again, it didn't give any error. See, on the left hand side, I have an 8-bit, and on the right hand side, I have 16. Ideally, I should do it like this. And last but not the least, they also have bit. So bit is 1 bit. Okay, so here I should say one. Okay, it's a 1 bit. So bit, byte, shortened int, and I think long int is also. These are all, I think, from your C++. Okay, so long int you will have to give 64 bit. So these are the storage things that they have done, right? And see, Verilog used to already allow things like this. Int, I'm sorry, log, what is it? Veg 3:0 x 3:0. We already know this, right? So what does it mean? It means there are four of these words. Okay? Each word is 4 bits long. You can also say 7:0. This means there are 7 words. I'm sorry, 8 words. Each has 4 bits. But what this guy is able to do is it can do multi-dimensional arrays. Okay. So system Verilog can handle any number of dimensions. You can have, in this case, I have shown 3Ds. That means you can have 3 indices. In fact, you can have a fourth index. Okay. So this is allowed in system Verilog. Maybe you need it in some cases. Maybe you want to write, you may want to model maybe a three-dimensional memory or maybe some image, which is the pixels are 8 bits and I have 256 by 256 image. So such things are possible, whereas I don't believe Verilog had that. You could go up to one level, but here it is any number. You can keep on going, although I don't think there is any real reason to do that. Is it clear to everybody? Then they introduce one more thing called a logic. So logic, let us say Q or something like. So this Q is a 1 bit storage, right? And it can be used in the place of either edge or wire. Okay, so can be used instead of edge or wire. So this is a very useful thing. See, earlier when I was trying to do many of these exercises, sometimes I used to forget that it is a edge, right? So I used to go back and add edge, right? If you had declared those as logic, none of this is required. So there is no sort of confusion. So instead of reg or wire, you can just declare it as it's. And logic will have 4 states: 0, 1, X, and Z. Okay. So if you want to say, you will see that it will print as ZZ. Okay. So the bits of logic are somewhat similar to the bits of reg, okay, or wire. So that is a convenience that they have provided in system Verilog. So use bit or byte or shortend, longend, or int if you are 100% sure that there is no chance of a zero X, I'm sorry, X or Z coming there. So suppose you had to declare a big array like this. See, ridge means unfortunately, you know what? It will have each bit will take 64. Each bit will take 2 bits. So the number of bits required here will be 8 cross 8 cross 8 cross 4 times 2. So the number of storage locations here will be very high. So if you had made it bit, then it will reduce by 50%. But then you cannot represent anything other than zeros and ones. So when you have large arrays like this, and you are sure that you will not have X's and Z's in that image, right? Suppose you are reading an image from some source. I don't believe you will have zeros and ones in that. I'm sorry, other than zeros and ones, you will not have anything in that image. So it is okay to use this. Is that clear? Are you guys following? There is a difference between, suppose I write bit 7 to 0 of P and bit P7 to 0. Okay. So there are two, both of them will work. These are all, both of them are accepted. There will be no error. But this guy, from a storage perspective, this is better. Okay. So what will happen is it will store it as 1 byte. It will store it as 1 byte, and the individual bits of that byte will be used to represent P0, P1, P2, P3, etc. Okay. So this is storage efficient. On the other hand, this one, though you are using it only as a bit, right? It will use up 8 bits, 8 bytes. Okay. So only one of those bits will be actually used to represent the bit. The remaining are wasted. So this is storage inefficient. But from an access viewpoint, this will be slow. Okay. So if I say bit I, right, then it has to sort of go and access the ith bit, using some masks, etc., etc. Okay. So I have a byte, and somewhere in that there is a small one bit that I have to extract. So accessing that will be, it will take time on a computer. Right? Whereas here it is very fast because you have stored it in the maybe the least significant bit of that byte. So extracting that is very fast. And you should understand that there is a subtle difference. So if you are wanting more storage efficiency, use this method. If you are looking for more faster simulation, then you can use this. In this example, you may not notice anything, right? Because it's a very small, trivial example. But suppose you have a large circuit that you are trying to simulate, then the small things will possibly get you a good amount of storage efficiency and speed and all that. Understand? So when your simulation is very slow, then you may be asked to check what can be done about the speed, right? So if you modify some of these method, from this method to this method, the answer, see, it will still be accessed as P of I. So for example, I can write for z equals 0, z less than 8, z, by the way, z plus plus is allowed. Okay? In system where they allow z plus plus. You don't have to write z equal to z plus 1. Similarly, minus minus is also allowed. So you can write p of z equal to 1 or p of z equal to 1. If they are both allowed. As I mentioned, small p of z, it will take a lot of time to do this because you have to go to the z bit in a byte and change it to 0. Whereas here, the entire byte is changed to 1 or something like that. So there is no, it will be very fast comparatively. That clear? And I think they have allowed struct, etc. So struct is allowed. Okay. Like in C language. Okay. So comp means a variable which is has a structure. So inside that there are two variables. Both are real variables. One is called the real part and the other is the imaginary part. So this may represent a complex number or something like that. So here you could go and say comp dot real part equals 11.5. Comp dot imaginary part equals minus 2.3. So that is how you access, just like in C language. Okay. So comp is a structure. It has, you can add other things. Inside you can have arrays if you want, right? Like bit, maybe x of 10, bit 7 to 0 up to. So all these are okay. And you can access them just like the way I told you, right? So comp dot q of I or comp dot x. I don't believe this was there in very long. So real is a um, double precision real number. It takes 64 bits, whereas short real is also allowed, which is single precision. Okay, short real SR. Okay, so in case you are happy with 32-bit precision, you can go ahead and use short real. It will be storage efficient. So they have short real and real. I don't think there is any long real. You can also define a type. Okay, for example, you can say type def reg 3:0 as nibble. Okay. And later you can say nibble n. Okay. So this will create a 4-bit register for you. Okay. So wherever you want a 4-bit, you can use this. Once and for all, you have declared a 4-bit register to be a nibble. So these are very helpful. So System Verilog has made many changes to the data types, fundamental data types. So some people call this as factoring. This is unpacked. So if you put on the left hand side, it's packed. If it is on the right hand side, it's unpacked. Got it? Let me save this also for you. System will log data types. Okay. This is not a useful program. It's some junk. Okay, but it tells you that there are different data types. Task and function were already available in very long. Okay, and they continue to exist in system very long as well. A task is a like a subroutine. A function is like the C function. Okay, the function has a return value, whereas a task does not have a return value. For some reason, they support both. One of them would have been enough, uh, but they have both. So let us use a task or a function. So when you write a function, you have to specify the name of the function. Okay. Let us say I'm going to return the square root. Um, Let us say given Euclidean distance, it returns a real value, okay, and takes as input, let us say a point. Okay. Let us define a point which is a type def. So point has been defined to be a struct with two values, real x and real y. So x and y are real numbers. They are part of a structure, and I would like to call this as point. So I have 2 points that come. So one is point P and the other is point Q. I think you can say point P. And it returns a real number, which is the distance between the 2 points. Function end function. Name of the function. What are the inputs to the function? And what does it return? So in this case, we have to calculate P dot x minus Q dot x, and we have to square it. Similarly, P dot y minus Q dot y, and we have to square that. Then finally, we have to take the square root of this. So square root is through SQRT. So it's a built-in function. Okay. And this is the value you want to return. So that is how you write a function. To use it, we can have something. Let us say we have point, let us say point one, and then one. I'm not sure how to do this in one go, but this will work. 1 dot x is 11.5, 1 dot y is minus 23.1, 2 dot x is minus 11.3, and 2 dot y is 43. Then we can say display distance equals, you can pass Euclidean distance, and you can pass the 2 points, namely 1 and 2. Distance. It is printing some distance. I hope this is all correct. So that is how you generate a function. Okay, everybody understood? Function, it is just like C language. Okay. In C language, we don't write function. We simply start by saying it's a int and name of the function and all that. But here they have given this function as a keyword and end function as another keyword. A task is very similar except that it doesn't return anything. It will do something. It may print things, etc. But it doesn't do any return value. Is that clear? So let me give you this as well. This is also, this is only in Verilog. Okay, this will not work in. So you can use functions to simplify your code. If you are planning to do something again and again, then writing a function will help. Okay? These are mainly for your verification only. Okay, you cannot give all these things in your what do you call this synthesis and all, you can't do. Okay, you cannot synthesize this code. This is meant only for verification. See, the designer may have developed a program for Euclidean distance. Okay? Let us say GPS coordinates are given between 2 points and you have to calculate the distance. See, that requires a lot of hardware and all that. Okay. But for verifying the hardware, it's no big deal. We can write a program like this. So this is like C programming or C++ program. Okay. It's very hard to write that floating point arithmetic, etc. I mean, you try to design a floating point arithmetic hardware. It is not so easy, but it's fairly easy to do it this way. Okay. If I want to write a task, let us say we write a task which display distance to origin. It takes a point P. So given a point P, it will display the distance to origin. Okay. So you will say dollar display distance equals percentage, and here you can say dollar square root of p dot x square plus p dot y square, right? So some sort of a trivial procedure. But typically, a task may have several things going on. We may write a number of. So I never called it task. Sorry. Okay. So we have learned some basic data types in system Verilog. There are many others. Okay. See, for example, there are strings, which was not there in your system Verilog. Module test and module. So you can say string, let us say str, and you can assign it to some value str equals hello world, and display strings. See, unfortunately, even these were not there in Verilog. So it's somewhat complicated sometimes. Okay. So it's good to have some of these data structures. It makes life a little bit easy. Okay. Then you can say display length of percentage is equal to percentage D. Okay. So I think you can say things like so it's a function that you can call on str. Okay. Dot length gives you the length of the array, length of the string. So you can see hello world it was printed, and length of hello world is length. See, you can also print string dot lower and all those things. You can convert it to lowercase, uppercase, things like that. Okay. So I don't remember all of them, but you can say dollar display percentage is string dot lower or something like that. I don't remember it is lower or what it is. Too lower maybe, huh? Too lower. Hmm. I'll tell you tomorrow. Yeah, I forgot how. So there is one two lower and two upper is what I remember. Hmm. I don't recall exactly what the syntax is. So if you want to find out yourself, I'll show you where to look. So go to search for system Verilog manual or user manual. Okay. So this is a good place to look for, this reference. This is the language system Verilog is maintained by Accelera, the company, and they also maintain Verilog. Okay, so they are the owners of the two languages. So you will realize that it's a very large language. So this thing is a few hundred pages. Okay. So it starts with literal values, data types, arrays, and all kinds of mm, data declarations, attributes, operators, and expressions. Okay. So all things are provided here. Okay. So you will see that it is pretty, big. So maybe around 400, 500 pages are there. Okay. But the nice thing is, if you go to that appropriate section, right, like tasks and functions, right, very good examples will be given. Okay, so you can quickly understand how they are doing. Okay. See, for example, string, right? I don't know string how to search. Let's see here. We talked about packed and unpacked arrays. We talked about multiple dimensions of arrays. Right? Strings are fortunately there will be too many things. There will be a lot of places where it doesn't seem to stop looking and it finds something. Too low as well. It's just too low. I shouldn't have put the underscore. Okay. So this is how you define strings. Okay. As I mentioned, they have. So this is how you initially define a string. String followed by the name of the variable, and you can initialize it right there. Like string, my name is Johnson. See, the examples are very nicely done. You can define a single character like this, byte C, Then there are 11 bytes in this. I'm sorry, it's a 10-bit array initialized to backslash x41. So in addition to 8 bits, it will initialize it to 3 zeros. Okay. I don't know why anybody would do something like that, but they have given how it behaves. Here they have taken a 2D. So H has 1 cross 4 multiplied by 7, 8 bits. So when you assign it to hello, what they are saying is it will split like this. So it assigns it to H followed by hello. So you have to go into all this. So it's unlikely anybody will do this kind of coding, okay? But they have shown you all possibilities. This is a language reference manual. So you should not try to learn to code like this. That's terrible, right? But this is some example. See, for example, if you want to repeat the word hi 5 times, you can do it like this. Okay. You can compare strings. Okay. Then you can concatenate strings. You can put a multiplier and put a string. So if you say 5 times some string, it will create a string where this this is repeated 5 times. Okay. You can access a specific character of this string. And then finally with methods. So length gives you the length of the string. You can change one of the characters of the string and so on and so on and so on. You'll have to read this carefully in case I don't recommend that you read all the I don't even know all the things that are there, right? I will come and look if I feel the need for it. Okay, so it's not possible to read all the things and understand. Okay, it will be very boring. Okay? So just be aware that there is a string data type, and if you want to use, see, you can do ASCII to integer, ASCII to hex. Okay, that awareness helps. Okay, if you didn't know, you will start writing your own code for all this. Okay, it's not required. Right? So when you have to use ASCII to integer, before you write your own code, just check if something is like that is already there. Okay? So the chances are somebody, I mean, these are all already supported. In addition to that, see, there may be people out there who have developed, libraries and so on, and they share it in GitHub and things like that. So you are also welcome to reuse some of the stuff that others provide generously, right? So tomorrow when we meet, we'll talk about more data types. There are many more, as you saw, right? So there is an event data type, right? And then there is an interface. So there are many things like this. So we'll go through that, and also we'll do some exercises. Okay. Any questions before we break? It's about 9:48. So I'll be happy to take some questions. We have about 10 minutes for Q&A. Any questions? Can you repeat bit? Oh, somebody has asked a question. Bit is a one bit data structure which can take either 0 or 1. Okay. Is that clear? Dave? Bit X means X can take either 0 or 1 only. Sir, how can we access the program for references like while practicing? What do you mean by that? The ones which I am sending, that they will make available in Canva. Okay. So they will put it there. Bit and real. Real is a floating, whatever you call as double in C is real. Okay. Whatever you call as float in C is short real. Okay. Is that clear? Like codes. Okay. Oh, you want to practice, over and above what I'm giving, is it? Um, Let me see. I mean, want to practice, I can give some reference. I have been giving no. I have been giving you all these exercises. So that is what you have to do. Today also I gave some exercises. Okay. So please do those exercises. What else? Anything? Anybody has any questions? And here also you will get a lot of good snippets. Okay, they are not entire programs, but you will find pretty decent, small code blocks. Okay, that is enough to get to start. See, for example, see here they are explaining. Yeah, I may not have mentioned this time thing. No? See, when I was using things like pound one and all that, right? If I write pound one, I mentioned to you that it wait for 1 unit delay, right? Now, what is that 1 unit delay, right? So you can Verilog allows you to say what that 1 unit delay is. So for example, here I can say time scale. You can say 1 millisecond, okay, 1 nanosecond or something like that, or 1 microsecond. Okay. What this means is whenever I say pound one, it means 1 millisecond. If I write pound five, it means 5 milliseconds. So in this case, when I said clock changes every 5 units of time, it means it changes every 5 milliseconds. And this thing shows, the smallest time between two events. Okay. So if event E1 has occurred and another event occurs at E2 very close to E1, the minimum distance can be only 1 microsecond. Okay. There can't be any other event between E1 and E2 within that 1 microsecond. Okay. So if such a thing occurs, then it will not be considered. When you have things like always add pause edge, etc. If those events are happening faster than 1 microsecond, they will not be considered. The resolution is 1 microsecond. So this is something that you need to. Yeah, I'm going to say send all that code, man. See this will be sent, and they will put it up in that website. Let me do that right away so that I'll send it to professor. What else? So we'll continue tomorrow with more data structures and so on. All right. Good night to all of you. I'll see you guys tomorrow.
Thank you, sir. Good night.
All right.